All right. So the question was, why did I mention that in many practical or modern cases, the image processing is done by not linear and shift invariant systems, but nonlinear or shift varying systems. And the answer to that is because of the input characteristics. The characteristics of an image just changes from portion to portion, and the best way to continue with that one, to adapt to that, is by making a shift varying system or a nonlinear system. And stability or causality is also not a big issue. I mean, not only non-linear or shift varying systems, we may have non-causal systems or unstable systems as well, which wouldn't be much of a problem in images, because in images, we cannot talk about a causality. It's irrelevant to talk about a causality. Think of a pixel in the center. To the right or to the bottom of it is the non-causal portion belonging to the future samples, whatever the future is. There is no time. There is only horizontal and vertical axis. Therefore, it's perfectly safe to use the future samples as well as the past samples, because we have every sample in an image. It's in our hands. So that's the answer to that question, is because of the characteristics. But the mathematical way of working on those things is difficult. So just like what we do in dynamic systems, we for nonlinear systems, what we do is maybe locally linearize or locally try to make it shift invariant, and then make a process on that and change the system to another portion of for another portion of the image to some newer parameters. And with those new parameters, now we can use it as a different system. And we are going to use, I mean, digital image processing. And people usually use computers for processing. So a computer can do equally the linear and the nonlinear systems. We don't have to apply resistors, inductors, capacitors, or such sort of linear things. Linearity and shift invariance is for the analysis purposes, for understanding the mathematics behind it. And for that, it's best to linearize the system, locally linearize, and try to understand how the system works. That's why in image processing, I told you that many of the practical systems are not necessarily LSI. I hope it makes sense now because of the signal and because of the tools that we are using, which is the computer that we have, which they can do just anything. But nevertheless, that was a good starting point, because in order to analyze the behavior, we still have to linearize and or assume that there is a linearity and shift invariance because of the mathematics. And here's the mathematics that we are going to use right now. That is the linear and shift invariant systems that we will be talking about. Linear and shift invariant systems. We have seen that these are systems which contain the two important properties, linearity and shift invariance. The nice thing about linear and shift invariant systems is that they act beautifully for not only points and their corresponding point spread functions. So we have a point going into the linear and shift invariant system, making a point spread function, which can be considered as the impulse response. And from here, we concluded that if X is the input to the system, to the same system, then Y is the output that can be obtained by convolving X with H. I'm not putting the time arguments or space arguments here, but it is a two-dimensional convolution, of course. So this is one good thing that linear and shift invariant systems help us because of this convolution thing. And the terminology convolution used to be a boring and an old-fashioned terminology, but together with the introduction of deep neural networks, which act locally, now the term convolutional neural networks came into the picture, which really uses convolution, and the convolution coefficients, the point spread functions, are back propagated and adapted using a learning algorithm. And the reason that they use local features is just because of the things that I have just said. Because in an image, the local features contribute to the shape descriptors like edges, corners, or circular shapes, etc. So there are shapes and they are descriptors and they are local. We don't really have to look at the whole image and take it as a dramatic and a very large neural layer and connect every pixel from every point of this image to the every pixel of the next layer of the neural network. Because the point here belongs to the background wall, whereas the point here belongs to a pixel from the backside of the book. So why am I trying to connect the information from both of them? That doesn't make sense, right? So, and because of that, convolutional neural networks, now the term convolution became popular again. But when I searched for that term on the internet to find some video explanations in my undergraduate signals and systems course, I was surprised and, well, not very surprised, but disappointed a little bit about not being able to find the convolution animations that in the undergraduate signals and systems we have seen to show to the students. But the first results were necessarily belonging to convolutional neural networks. That was an interesting deviation or a fluctuation from the mainstream information. The meaning of a term just deviates in time. But as I say, it's still the same definition. It doesn't really change much as an underlying idea. Now, the second issue about linear and shift invariant systems is according to their output or response to a particular input. And for that one, I'm going to use not a discrete time two-dimensional system, LSI system, but a continuous time one, because, you know, it's easier. In fact, I'm going to use a 1D continuous time, linear and time invariant system, just to help you remember the concept that was in the third year or second year signals and systems courses that you have seen. And that is the response to this complex exponential. You remember that in the first weeks, we have discovered how such complex exponentials or complex sinusoids behave in 2 dimensions and what kind of periodicity they have. That was an important issue. The 2-dimensional complex exponential was, or a sinusoid was an ondula shape, a wave shape, as you may remember. The reason that we were focusing a little bit too much on such sinusoids is somewhat because of this, in order to analyze what's happening here, or better analyze what's happening here. So what is this? It's a complex exponential, and according to the Euler's expansion formula, it's a cosine omega t plus an imaginary sine omega t, right? We know that. And from here, we also know that the cosine is consisting of e to the j omega t plus e to the minus j omega t divided by 2, and sine omega t is e to the j omega t minus e to the minus j omega t divided by 2j. Okay. This also gives us an interesting impression that essentially all types of signals, not only this complex exponential, can be split into 2 components, one of them being an even function, symmetric, the other one being an anti-symmetric, an odd function. okay, like this cosine and sine. But you can do it for any x of t, actually. So this was just an expression of what e to the j omega t looks like. But the issue that we are going to do now, sorry, excuse me, is what happens if I input this to this, right? This is something that we have briefly mentioned about. And we know that the output is, what was it? It was, let's say, A sub omega, which was something that depends on that frequency, the angular frequency omega, times e to the j omega t. So later on, we called it, we called such things as eigen functions or eigen signals of this system. It's essentially something like this. If you call it a vector x, and this system to be equal to a matrix, let's say A, and this is the scale. It's a scalar, it's a number. And this signal is the same as the input x. So everything really looks like A times x is equal to lambda times x. X comes into the system and it goes out of the system just by being amplified or scaled by a scaling function of lambda.
There is no phase shift, sir?
Yes, there is, and that is in the complex lambda.
It's included.
Yes, it is in this lambda or a sub omega. It is complex.
It's complex,
not,
okay.
If it is imaginary, then it means it's making a phase shift of 90 degrees.
But
it's
not
in general
complex.
just complex. So that's how we apply the phase. So we're not thinking about the phase and trying to incorporate it into the complex exponential. We don't need to do that. It is included in a sub omega. Because this way, it looks more like the eigenfunction, really. Because the input is an eigenvector. This x is an eigenvector of A. So from that analogy, we can say that complex exponentials are eigensignals of linear and time invariant systems, regardless of that linear time invariant system. As long as it is LTI, complex exponentials are eigensignals of that. They come in and they go out just by scaling with a complex number. Do we know what that complex number is? A sub omega. What is the eigenvalue, in other words?
I think it's the magnitude of H, maybe the magnitude
no,
of...
It's not a magnitude first of all, because it's a complex number, but you can derive it. You can always derive it. And I would like you to know how to make this derivation, because this derivation is one of the methods to prove the Fourier transform formula. For example, in PhD qualifiers or in any kind of tenure examinations, any scientific exam level, at some point, if you are, of course, more related with signal processing, otherwise, or control systems. For others, maybe they may not ask this one, but this question may be encountered by you. Derive the Fourier transform formula. And over there, you will have a few alternatives to do that. There are alternative ways to do it. But one way to derive the formula, the Fourier transform formula, is to use this. Because we know that the output here is actually e to the j omega t convolution with h of t. because of this linear and time invariant system. So let's write it. Let's write the convolution. So y of t is equal to e to the j omega t convolution h of t, which is from minus infinity to infinity. E to the j omega t is the x of t. X of t minus tau I'm going to write, which is e to the j omega t minus tau, then h of tau d tau. I can write it like this. And over there, from there, I can split the exponential into two parts, e to the j omega t, e to the minus j omega tau, h of tau d tau. Okay, I can write it like this. And the integration is all over tau. So this one is
Outside.
independent from tau and it can be taken out. And it will be, let me continue from here, e to the j omega t integral from minus infinity to infinity, e to the minus j omega tau h of tau d tau. And this is the frequency response of the system with an impulse response h of t. That is a sub omega, as I previously indicated. But essentially, it corresponds to h of omega, the frequency response. And the frequency response is obtained by the Fourier transform of h of t. So this must be the Fourier transform of h of t. The Fourier transform of h of t.
We can write it as the magnitude times the exponential of the phase. I mean.
Oh, yes. Yeah, of course. But when you just include the magnitude and the phase, what you get is the Fourier transform itself. Yeah, it's not really the magnitude, but the magnitude and the phase, which means the frequency response or the Fourier transform of h of t. So, in short, complex exponentials are eigensignals to linear and shift invariant or linear and time invariant systems. So, how can we use them? In short, for finding their responses. How can we use the frequency response? As you see, for every complex exponential at a certain frequency, it produces h of omega at that certain frequency times the same complex exponential. Let me open a new page and try to explain what I mean. E to the j omega 1 t produces e to the j omega 1 t times h of omega 1. Okay? That is the input and output relation of a linear and shift invariant system. So how about a times e to the j omega 1 t? It will produce a times h of omega 1 times e to the j omega 1 t at the output. How about if I say b times e to the j omega 2t and add it to the input, then the output will be the same thing with this time omega 2, like this. Right? So what I'm doing is, at the left-hand side, if I can split my representation into complex exponentials, each of that complex exponential will have a corresponding response. Okay. So what is a way to split the input into complex exponentials? How do you write a signal in terms of a summation or an accumulation, an integration, whatever, a combination of complex exponentials? How can you do that?
Fourier series, maybe?
Fourier series, maybe, exactly. Which will give you a k from minus infinity to infinity, e to the j omega k, the corresponding frequency, which is actually 2 pi over the fundamental period times k. Okay, I will write it later. T, for instance, the output will be summation k from minus infinity to infinity, ak h omega k e to the j omega k t. So the input-output relation has this kind of a behavior. Now, these are the Fourier series coefficients, and those Fourier series coefficients are, as you see, multiplied with the corresponding frequency response of the system at the corresponding frequency. But there is a more general way of doing it. It doesn't have to be periodic. If it is periodic, you can just expand it into Fourier series, and the input-output relation is found very, very easily. But we also have the Fourier transform. It doesn't have to be periodic, which is a more general way of writing things. And that is x of omega e to the minus j omega t.
The omega.
Omega, excuse me, it's not minus.
It's plus, because the inverse.
Yes, this is the inverse Fourier transform. So x of omega is the Fourier transform, and this is the representation of the signal. And from here, the output is therefore, again, x of omega, and omega is from minus infinity to infinity. The frequency is sweeping, okay? And for every frequency that is sweeping on x of omega, for exactly the same omega, term by term, we are multiplying it with h of omega, right? The same omega times e to the j omega t, where this e to the j omega t is omega is also the same omega from minus infinity to infinity, the omega. Okay, this is the input-output relation. And now we observe something that we expect already. This is y of t, therefore from definition, this must be y of omega, which tells us that in the frequency or along the frequency axis, if I multiply my signal's frequency representation, which is the Fourier transform, with the frequency response on the omega axis, term by term multiplication, the output will be corresponding to the frequency representation of my output, y of omega. That's why convolution in time will have a Fourier transform that corresponds to multiplication in frequency. It's not y, it's h, excuse me, like this. All right. So these are, this is just a crash course on signals and systems and the Fourier transform and where it comes from. The Fourier transform, Jean-Baptiste Fourier himself discovered it from a heat equation, which is a little bit different from these concepts, but of course, due to later discoveries by Laplace and Dirichlet and other co-workers and himself, the relation to linear and time invariant systems or linear and shift invariant systems in 2 dimensions are discovered, and the relation is established between linear and time invariant systems and the frequency response because of this complex exponential business, because complex exponentials are a unique class of signals which are very useful for describing the behavior of a linear and time invariant systems. But when they come into a system, it goes out of the system almost the same, except for a scaling with a complex number. And from there, we come up with the definitions of the Fourier transforms and all these formulas. Now, these formulas are also valid in 2 dimensions. Now we can safely proceed with the 2-dimensional situation. I will try to write down why it works that way, because the convolution and the eigen signal behavior is also retained. It also exists in 2 dimensions as well. For example, this time I will proceed with the discrete time case in 2 dimensions, because in 2 dimensions we usually have discrete time signals. So let's think of it like this: x of n1 and 2 going into a system whose point spread function is h n1 and 2, and the output is y n1 and 2. And if you try to just say that this is a complex exponential in 2 dimensions, e to the j omega 1 and 1 plus omega 2 and 2. This is the complex exponential in 2 dimensions, which is a wave function, as we have seen in the first weeks. This wave, when it goes into the system, the output will be y of n1 and 2. Let's find it, and that is by convolution. Y of n1 and 2 is equal to a double summation because of the convolution in 2 dimensions, if you may remember. For all k1 and k2, e to the j in parentheses, that's a cumbersome operation a little bit because everything is doubled. Omega 1 and 1 minus k1, it's like t minus tau if you think of it, plus omega 2 and 2 minus k2. This is also t minus tau along the other axis. So I wrote like x of t minus tau, or x of n minus k, and then I will write hk, h of k1, k2, and we can now split this into separate terms, like e to the j omega 1 and 1, and e to the j omega 2 and 2, and e to the minus j omega 1 k1, e to the minus j omega 2 k2. I can just write it like this because of the Euler's formula. It's not the Euler's formula, it's the exponential in the form of multiplication for separate exponents. So then I will bring this part out of the summation because it has nothing to do with k. The summation is all from k1 and k2 being minus infinity to plus infinity. So it is not related with k, they are n's. Let's take them out. E to the j in parentheses omega 1 and 1 plus omega 2 and 2 times, let me open a huge parentheses, it's a double summation of k1 and k2 e to the, I will start from not the exponentials, but let me first write h, k1, k2, e to the minus j in parentheses omega 1 k1 plus omega 2 k2. Let me write it like this. Now, as you see, we have input this signal, and the output is this signal, where this part is the same as the original input. So we can say that this is therefore
2D Fourier transform.
Yes, this is h of omega 1, omega 2. Okay. It's therefore the 2-dimensional Fourier transform. 2D discrete time Fourier transform. It is discrete time, therefore it's the discrete time Fourier transform. Now, at this point, although we will come to the discrete Fourier transform topic later, which is important, while we are discussing the image transforms, because DFT, 2-dimensional DFT is an image transform. It's wise to warn you that this is not the two-dimensional DFT. It is the two-dimensional DTFT. What is the difference between a DFT and a DTFT? Have you ever thought of it that way? Do you know DFT, discrete Fourier transform, which has a fast implementation known as FFT, fast Fourier transform?
It's the DFT.
Yeah, what is the DFT? And what is the difference from this one and the DFT?
The DTFT is continuous in the frequency domain, but the DFT is discrete.
Yes, exactly, exactly. This is, this Fourier transform produces a continuous variation in frequency. It's h of omega, it makes h of omega. It doesn't make capital H of K, okay, a discrete index. So this thing is still hypothetical for computers. For computers, they cannot, you cannot evaluate the discrete time Fourier transform. Using computers, the only thing that you can do from the discrete data is to find the discrete Fourier transform, DFT. That is something that you can do because it's a discrete to discrete mapping, discrete in space, discrete in frequency. It's an n by n matrix kind of multiplication. Whereas this one is really a Fourier transform where you plot it on the horizontal axis continuously, and the axis is the frequency. So this is not DFT. Okay, be careful about that. Now, this discrete time Fourier transform has some properties that every student or every image processing student must be aware of. Let's proceed with those. To the DTFT properties. The first property is also the most important property, and it is inherited from the one-dimensional discrete time Fourier transform. And the normal discrete time Fourier transform is 2 pi periodic, if you may remember. And you may ask yourselves why it was 2 pi periodic. Because the separation between the signal samples is by one by one. So you cannot increase the frequency arbitrarily. The frequency will come back to itself, repeat to itself after 2 pi radians in the frequency increase. After 2 pi radians, your sampling between these two samples, which are separated by 1, will be sampled again. You don't have anything in between. Now, let me ask you or show you a signal with the highest possible frequency in discrete time. Can you plot such a signal with the highest possible frequency? On the n-axis, let's draw them one-dimensional, okay? I'm going to draw x of n, and it will be the highest frequency that is available to you. What kind of a discrete time signal can you draw? If it is continuous time, you may want to plot crazy-like oscillations, okay? And try to squeeze the sinusoid or the oscillations or noise-like structure as much as possible. It will indefinitely increase the frequency all the way up to infinity. That's possible. But in discrete time, there is nothing higher frequency than this one. Okay. You cannot increase the frequency further from this. Do you agree with this? All other signals have lower frequency than this one. This is 0, 1, 2, 3, 4, 5, 6, 7, 8, etc. -1, -2 along the time axis. One positive, one negative. It may be plus or -1. It doesn't matter. What is the frequency of this signal?
I was thinking more of the delta because the delta has a Fourier transform of 1.
Yes, it also, that's right. That also has the highest frequency possible. but it also contains all the lower frequencies as well. This
Yeah.
signal does not contain any low frequency. It is pure sinusoid, and it is the highest frequency sinusoid with a single frequency. And that single frequency is the highest frequency. That's what I'm saying. Of course, for example, you can draw a unit step function, which also has all the frequencies all the way up to the maximum. But this one is the maximum, that maximum frequency is here and nothing else.
We will have only delta at the max, that's all. Right?
Excuse me? I
I
didn't
said,
get.
you said this signal will have only one component at the highest frequency.
Yes, one frequency.
Mm-hmm.
Mm-hmm. And what is that one frequency? Frequency is pi.
Mm-hmm.
So pi is the highest frequency. Just try to visualize or try to draw a sinusoid behind it. Okay, just try to draw a hypothetical sinusoid and assume that these points are the samples of that sinusoid. Okay, if you try to increase the frequency of this red dotted sinusoid a little bit more, if you want to squeeze the sinusoid by increasing the frequency, but keeping the sampling instances at 0, 1, 2, 3, etc., you will notice that you will come up with some further like envelope oscillations, which contributes as lower frequency components. And as a matter of fact, if you increase the frequency of this red twice, okay, just squeeze the sinusoid to half of the period, you will notice that it will have this, and then this, and then this, and then this, and this, etc. And when you sample them, they will give you this, 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 which is actually zero frequency, the DC. You see what I mean? The samples will converge back to omega is equal to 0 of the discrete version. Omega is equal to 0. But what is the frequency of the underlying red sinusoid? It's 2 pi.
2 pi. Mm-hmm.
So pi reaches to the maximum oscillations. After pi, it decreases and goes back to, after pi, it goes back to 0. At 2 pi, it comes exactly the same as the 0 frequency. After 2 pi, it further increases once again and reaches to the maximum at 3 pi. And this is coming back to 0 at 4 pi, etc. So all the even multiples of pi, including 0, will correspond to the 0 frequency, and all odd multiples of pi, 2k plus 1 times pi, will be corresponding to the highest frequency. And this structure makes the DTFT, the discrete time Fourier transform, to be 2 pi periodic. Whatever you have at around 0, you also have it around 2 pi, you also have it around 4 pi, and whatever you have around pi, you also have it around minus pi, minus 3 pi, plus 5 pi, etc. So everything becomes 2 pi periodic, and only, let's say, between minus pi and pi is the meaningful range for you, because pi is the highest positive frequency, minus pi is the highest negative frequency, and 0 is in the center, it's the lower frequency. From lowest to the highest, you see everything in a single plot. So people just tend to plot the Fourier transforms or their magnitudes, whatever, like low pass filters, high pass filters, etc., only from minus pi to pi, because after that it just repeats itself. Okay, and in 2 dimensions we have the same property of this, what I have talked about. Oh, sorry, something happened. Excuse me. A computer, some message came. So in 2 dimensions, the same thing is valid, and the way to write down that one is the 2 pi periodicity is h of omega 1 plus 2 pi k omega 2 plus 2 pi L. For k and L, every integer is equal to h of omega 1 omega 2 for all k and L being integers, positive and negative integers. So this is a 2 pi periodicity. Now, the way to visualize such a thing is maybe a little bit difficult, but a low-pass filter, for example, from now on, we will try to illustrate. I have to draw something large here. And let's say this is 2 pi, this is 4 pi, this is pi, this is 3 pi, etc. So every dot would correspond to an increase by pi. This is an example of a low-pass filter. For instance, this is a low-pass filter. Maybe I should draw it with a different color. As you see, it's not it's not extending all the way to pi or minus pi, but it's somewhere between 0 and pi over 2, maybe, I don't know. So, and it's a surface, it's a two-dimensional surface. So if you tilt this thing a little bit towards the screen, you will see that I have a box here, okay, with some certain height. And that height, it may be varying height, but that surface of the top surface of the box corresponds to the passing amplification ratio for the corresponding frequency of omega 1 and omega 2. So this is a simple way of drawing a low-pass filter. Of course, this is not the only low-pass filter. It could also be a circular shape, okay? But this seems to be, if it is uniform all ones along this box shape, then it looks like a separable low-pass filter whose Fourier transform we are very familiar with, because it's a rectangular function along the omega 1 direction. If you cut this and draw it in one dimension, it will look like this. So it's a rect function, rectangular function. What is the Fourier transform of a rectangular shape? Do you know what the Fourier transform looks like? H of t over t, or n, doesn't really
Maybe the
matter.
sinc function? Not the
Yes,
sinc?
it will. Yes, it will be a sinc function. So on the frequency axis, it will be the sinc shape like this. So the wider this rectangle, the narrower the sinc, because they are inversely proportional in frequency and time. And the narrower the rectangular function, the wider the sinc becomes. Now, I would really like you to consider the limiting case. What happens, for example, if the rectangle function that I make is indefinitely wide, then it means it is 1. H of t is 1. It means. What is the corresponding Fourier transform of that? It will be indefinitely narrower version of this sinc. While becoming narrow, it's also extending in the upper magnitude. So it converges to what?
Impulse.
Impulse. Because the Fourier transform of 1 is an impulse. That's something that we already know. So an impulse can also be considered as a sink shape, which is being indefinitely squeezed without changing the area underneath. Therefore, the peak value also increases. That's how we obtain an impulse. It's an alternative form of thinking of an impulse. The other one, let's make this time the rectangle as narrow as possible, but its energy will shrink. When we make them narrower and narrower, this sink shape will be wider and wider, but it will fail down to zero. But let's also make this rectangle not only narrower, but this time taller. So let's keep the energy of the impulse the same. Not impulse, rectangle the same, which will eventually converge to an impulse. When you squeeze the rectangular box from both sides, but while keeping the area underneath, it will blow to an impulse. Then what will be the sink shape? It will be wider and wider and wider, and it will stretch all the way up to a uniform value of 1. That's why the Fourier transform of an impulse is 1. Okay, they have that kind of a dual relation. But anyway, let's now focus back to our two-dimensional case. If you have this kind of a rectangular shape, then it means you have this thing as a horizontal slice whose Fourier transform is like this. And if you cut it vertically, it will again be this kind of a shape. Again, a rectangle will come out if you just cut it from here. Then it will also give you another sink shape. And when you combine those sink shapes, it will be a horizontal sink shape superposed with a vertical sink shape in a rectangular way, which is different from another. Why am I unable to do it? Yeah, okay. Another shape, alternative shape. It's acting crazy. Okay. This one is also a low pass filter. Let's say that it's perfectly circular. Let's assume. Then when you tilt it a little bit and look at the profile, it will look like a cylinder. Okay. Now, what does the Fourier transform of that look like? Again, when you cut horizontally, or what does the inverse Fourier transform look like? If you cut it horizontally, you will notice that it's again a same rectangular shape, so its Fourier transform is sink. And vertically, again a rectangle, it's again a sink. So what is the difference between the Fourier transform of the top rectangular box and the below cylindrical box? The difference is the Fourier transform of the below shape will look like a sink in all directions, but it is rotationally symmetric as well. So you take a sink shape, you take this shape, and then rotate it, rotate this omega axis, okay, all the way around, and you come up with a surface. It traces a surface like this. And what you will get is called from here, sombrero. It's the Mexican hat shape, which is rotationally symmetric. But if it is from here, it is not sombrero because it's not rotationally symmetric for this one. For the below one, it is rotationally symmetric. Now let's come back finally again to our discussion. Since it is 2 pi periodic, as I say, we don't have to draw them, but we have to implicitly assume and observe that actually we have the low pass passing entities all the way here, 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 and of course here, here, and here, and here, etc. We have them everywhere. We have infinitely many of those. Okay, we understand what I'm talking about. These blue boxes are 2 pi periodic, both horizontally 2 pi and vertically 2 pi. Okay, and that property you must always be aware of, because very soon we will start upsampling and downsampling our 2-dimensional signals. And when we are, for example, making an upsampling means it's like making your signal wider. Okay, you are inserting zeros in between every other sample. X0, Y0, Z0, etc. You insert zeros, so you make it wider. And when you make wider, we know that in 2 dimensions the same. You have to make the Fourier transform to be narrower. So you don't only narrow down this central rectangle, but some portions from the right-hand side rectangle will also start arriving there when you shrink those things, or from the top they will arrive, depending on what kind of upsampling you're doing. And when you are doing downsampling, similarly, when you expand something, when you expand this one, this portion will go to somewhere else, and this portion will go to somewhere else. But of course, in order to make them 2 pi periodic, we have to insert their 2 pi periodic versions again and again in all these 2-dimensional tiling. These tilings in the Fourier domain is a critical issue that you have to be comfortable with, because they will be essential for a lot of questions in your take-home examinations. Okay, we will be doing very nasty downsampling, upsampling, and filtering and things like that. This is for the system, but for the signal it's the same. The signal, for example, will look like, I don't know, maybe something like this. This will be our signal's Fourier transform, and therefore they also repeat themselves here and here and here and here. So when you filter in the Fourier domain by multiplying h of omega with x of omega, multiplying them, you're just like masking those green dashes, surfaces, in 2-dimensional frequency axis of omega 1 and omega 2. You're masking them with those blue boxes. They will just crop it. And everything beyond the box boundaries for each box will be just chopped off, and they will be eliminated. That's why it is low pass filter. The higher frequencies will be just eliminated. For example, if this is a low pass filter, it could be a high pass filter. High pass filters can be considered as the reciprocals of that. Just take these boxes and do not trace them, but instead trace all the places except those inside boxes. Everything beyond these boxes, all the remaining places, will correspond to a high pass filter, for instance. That's an interesting thing. And maybe the craziest thing would be a band pass filter in 2 dimensions. Try to visualize them. Try to draw example tiles on your mind for those things. I want to just stop at this point and give a break of some time, maybe, I don't know, 20, let's make it half an hour. Let's start at 11 o'clock, and we will do 1 more hour. Let's start at 11 o'clock. At 11 o'clock, until then, I would like to have some example Fourier transform shapes and things like that from the internet. I will search for them. I hope I can find them. And we will continue with our discussion afterwards. This is how the 2-dimensional discrete time Fourier transform looks. And this look is very important for us for our analysis purposes. First, let me ask you if you have any questions. At 11 o'clock, we will meet again. You may
So
collect your questions. Yes?
you said that in okay, in image processing we don't have the concept of time. So is it safe that I consider the N1 and N2 maybe as positions of the pixels instead of time? Maybe.
Of course, of course. In fact, that is more correct way of doing it. That's the correct way of saying it. But from signals, I'm just more used to calling it time. For example, discrete time Fourier transform, I say. Maybe it's safer to say discrete space Fourier transform, because it's not time, of course, you're right about that. But it's just the terminology. We know what we mean by that. Of course, they correspond to the positions and it's space.
Another question.
Yeah.
Okay, when we speak about 2D signal analysis, is it necessary that I'm referring to image processing?
No, it's not necessary. You may come up with any kind of two-dimensional signal. In fact, in the first few minutes of our first hour in this course, we talked a little bit about such things. You may come up with any kind of a data that has 2 degrees of freedom or 2 free variables. Inside the parentheses, the dimension is determined by how many parameters you have inside the parentheses, how many free variables you have. If you have 2, then it makes it a 2-dimensional signal. An image is just an example for that, but it may be some other thing. In fact, I may also try to show you some papers of ourselves, our research group, where we just constructed a 2-dimensional representation of another thing, which are voltage waveforms. Okay, from voltage waveforms, we cut one period of a voltage waveform at 50 hertz. So 1/50 seconds long, or 2/50 seconds. It may be twice the period. So we have 2 oscillations of a sinusoid, and we cut it from there, and we tile them one below one another, which makes a wave shape. That wave shape, we just constructed like an image, but it's not image, it's actually the voltages. Why did we do that? We did it in order to use or utilize the image processing tools to detect some voltage faults. For example, if the voltage waveform is not 50 hertz, but it is 50.001 hertz. And the sampling frequency is, let's say, 10 kilohertz. 10 kilo, yeah, let's make it 10 kilohertz. Okay, fine. So your computer is exactly 10 kilohertz sampling. So 1 second is containing 10,000 samples. And 1/20 seconds of each of them, you chop them and tile them on below one another to form an image-like thing. You will notice that if your signal is 50.001 hertz, the wave will be tilted like this, or like this, I don't know. Or if it is 49.999, then it will be tilted the other way around. So we are measuring that amount of tilt by image processing techniques, and we are therefore measuring very accurately how much the signal is deviating from 50 hertz. Normally it should be 50 hertz, right? But the smallest deviation you cannot detect by any other method. You cannot just take the Fourier transform and try to see the frequency over there because that much frequency resolution is not available in DFT, discrete Fourier transform. You cannot have it. But by using image processing, you can measure these angles, and these angles will automatically give you how much you deviate from 50 hertz. So you see, it's not image. It is actually the voltage. Or in biomedical signals, they are not images either. For example, think of a computed tomography or an MRI image, which gives you the interior, a slice of your interior body. you don't take the picture of your interior body. It's just a visualization of data. So such images are not really images as we know of. We don't see them using our eyes. But yeah, you can think of you can just extend the examples here. It doesn't have to be images. You may start collecting other questions, but right now I'll just stop the recording